All right, guys, so we're starting a new chapter. One of only a couple left this year. And if I were you, I would keep kind of maybe if you got a little bit of free time here or there, start chipping away at this review sheet. No sense of urgency at this point. I mean, literally, we've got 30 days-ish. If you did just 4 problems a day, 3 problems a day, between now and then, you've knocked out 90 problems. And then when we get to, plus you're going to have Monday all day in class. Well, not all day in class. For those 50 minutes in class, you'll have Monday to work on it because I won't be here. And then you'll have 3 full days, the last 3 full days in class, that Wednesday, Thursday, Friday before we start exams, to finalize things, ask questions. And of course, you got the weekend before the exam starts. And then you guys, 7654, your test would be on Tuesday. The second exam on Tuesday. So you'll even have Monday after school if you want to come in and ask questions or whatever. So in fact, honestly, my AP kids will be gone at that point. So if you wanted to come in here 3rd period or 6th period, you could do that as well, like on a Monday. If you're not doing anything in that class or you don't need to worry about that class, you could come in here 3rd and 6th and randomly ask some questions or whatever. So because there won't be anybody in here. But anyway, take advantage of these last 2 tests that we have. I really think that you can do well on them. The trig stuff that we're going to start today is pretty basic. I will say this about today. What we cover today, people tend to forget to study because we cover some stuff today, and then tomorrow we jump into actually the graphing of the trig functions, and people get so caught up with making sure they know how to graph, they forget to go back and review this day 1 stuff. A couple of these things you're already going to know, but a couple of these things you may not know. So make sure you remember to go back and look at this. All right. So what we're going to talk about today is a little formula and how to apply it. It's theta equal S over R. I actually do have an assignment sheet for you. Don't let me forget to give you this. But we're going to be dealing with radian measure. We're going to be dealing with sections of a circle, like finding area of different sections. And there's formulas that you can use for this, or there's good old common sense that you can use. And this formula right here is kind of the beginning of it. And this basically says, all right, you're going to have a radius right here, all right? And then you're going to have some kind of arc length, like from there to there, right? And then you're going to have some kind of angle from here to here. And the relationship between this theta and that S and that R is always theta equals S over R. If theta is in radians, get that down and star that. Because every year I'm going to give you a problem and people miss, to me, the easiest question on this test. For instance, I'll say, determine the arc length. And what is arc length? What letter is that? That would be the S. Determine the arc length if the radius is 10 inches and the angle theta is, tell you what, 60 degrees. You know, people did a little studying. And they remember the formula, and they come over here and they go, all right, well, theta equals S over R. So if theta is 60, and my arc length is what I'm looking for, and my radius is 10, they go, oh, S must be 600. And they circle that, and they're way off. Okay? Because what did I do? I use degrees. So what I have to do is change degrees into a radian value. Now, you should know that at 60 degrees, what is the radian value?
It's pi over 3.
Pi over 3. And if it's a unit circle value, great. What if it's not a unit circle value? What if it's something like 50 degrees?
Like over 180.
Yeah, then I'm going to have to convert it. And what is our conversion factor?
X over 180 equals.
Remember, it's like stoichiometry. I got to use something.
50 over 180.
Pi over 180. Why? Because pi and 180 are in the same place. Heck, you could use pi over 2 over 45. I mean, no, sorry. Pi over 2 over 45. Sorry. Pi over 2 over 90. You could use 360 or 2 pi over 360. You could use any spot, but 180 and pi doesn't have any fractions, so it's kind of nice. So I'm going to go 180. Sorry, I'm going to do pi and 180 because they represent the same location, so it's kind of the same angle. And then because 180 is a degree and pi, by the way, is not a radian. Pi is 3.14. You know that, right? People confuse pi with radians, and I'll talk about in a second what I'm talking about. Remember, the radian, I don't usually write the word radian, so it's not the pi that tells me it's a radian. It's the absence of the degree sign that tells me it's a radian. And I'll get back to that in a second. So right here, if I were to cancel, the degrees are going to cancel. I could probably cancel out or divide 10 into both, and I get 5 pi over 18, which is weird, but I come over here and I plug 5 pi over 18 in for my theta. And now when I solve for S, I get 50 pi over 18, which is going to reduce a little bit. But that would be my arc length. Are y'all with me on that? So make sure if you're using this formula that you're thinking about this. Right? Now, what are you going to do if instead of saying determine the arc length, I also ask you to find the area of the sector? Now, there's a couple area formulas out there. I'm going to be honest with them. Every year I look at them and I forget them. So I'm going to show them to you, and you can have them and use them if you'd like. But I don't ever use them because I'd rather use some common sense. But here are your two formulas for area of a sector. And sometimes they're nice. You get a 1/2 r squared theta, or you could use 1/2 rs. And again, if you use the 1/2 r squared theta, you've got to use what for theta? Radians. But I'm thinking this. If I want to know this right here, this area, can I find the area of the whole thing? And isn't that part a percentage of the area or a fraction of the area of the whole thing? And the whole thing has what degrees? And that has what? 50? So couldn't I just find the area of the whole thing? The area of the entire circle, that whole thing right there. If I found the area, it would just be pi r squared, right? So I would have pi times the radius, which would be r squared. And then what would I be multiplying it to find what part of this if my angle is 50 degrees? 50 over 3, like if that angle's 50, then that represents 50, the theta. I tell you what, I'm just going to write 50. 50 over 360. It's that part of it. So now I have the area of my sector right there, which is that percentage of the whole thing. Does that make sense? Yes, no? And if I clean that up, the nice thing is, look, I don't have radians because the degrees cancel. And I can plug the r equals 10 in there, and I'm going to get 50 over, I'm going to get pi times a 100 times a 50 over a 360. And I can cancel that 10 with that 10. And then and I can also cancel what? 4 goes into that 9, 4 goes into that 25. And I'm left with what? 125 pi ninths. Y'all with me? Now look if I were to use this formula right here. If I were to use this formula right here, I'm going to take half of the radius squared, right? But what am I going to have to do with my degree? I mean, with my angle.
Turn it into a radian.
Turn it into a radian. So when I turn it into a radian, I'm going to plug 5 pi over 18 in here, right? And look what I get. I get 1/2 times a 100 times a 5 pi over 18. And I'll be able to clean up some of this. 2 goes into that, 50. 2 goes into that, 25. And I get 25 times 5 pi over 9. So I can use this formula. It just requires me to memorize this formula. Or I can use this one too. But if you really think about it, this one and this one, if I replace theta with S over R, because that's what it is, if I replace that theta with an S over an R, one of the r's cancel, and I get that. That's just a good formula if you happen to have the arc length already. In fact, this is one that I think is worth memorizing, because if I give you arc length and I give you the radius, right, then you don't even have the theta to do it this way. So in this case, it'd be nice. You would end up having to go through this. So knowing that formula is great, but definitely this. If you know this, and you've got a relationship between S, R, and theta, and if you're missing any one of those variables you need, you can use it. But if I ever ask you for an area of a sector, please be careful. Also, sometimes I trick you up on a question, and I'll go, hey, if you cut out a piece of pie that had a 50-degree angle, right, and a radius of 10, and if you cut out that piece of pie, what is the area of the pie left? And I always have people that go, oh, the area of the pie left is 125 pi over 9. But what did they just find? The area of the pie that I cut out. What do I want to do here if I want the area of the pie left?
Whole pie.
Okay, I could do the whole pi minus it, but what if I didn't want to do the whole pie? Instead of using 50, what could I have just used? I could have just used 310, right? But your way would have worked. But if I just use 310 right there, that gives me the percentage that I actually have left. Y'all tracking with me? So I will get a different value there. But make sure you read the question, bottom line, and make sure you're answering what it is I'm actually asking about. But I usually ask a couple questions like that. It's on every single test. They're like 3 or 4 points apiece. And if you don't review it, it's like -4, and you don't want to be -4 right off the top. Because there's lots of little bitty things on the graphing the trick stuff that can get you. You know with me? Make sure you check these out tonight. There's a couple problems on your homework. Probably one deals with area, probably one deals with whatever. But the big key is this function right here. This only works if it's a radian. But if you're doing that other method where you're just finding the area of the whole thing and then multiplying it by the percentage or the ratio of what's actually being taken or used or whatever, then you really don't have to do your degree conversion to radians because the degrees are canceling out of this. Just saves you the trouble. Right? Okay. Couple other things. And this gets people too. I ask, and these are usually like part A, part B. So they're not worth a ton of points. But sometimes I'll say convert something like 2 pi over 5. And I'll say convert to degrees. Well, if I convert to radians by using a pi over 180, what am I going to do to convert to a degrees? A 180 over pi. Now, here's where you got to be careful. Not on this problem. If I wanted a degree, I'm going to put a 180 degrees over a pi. Remember, pi isn't the radian unit, right? But I can do that because stoichiometry says if these two mean the same thing, but just in a different language, just like inches and feet, degrees and radians, same thing, different language, I can multiply by that and cancel and see what's left. And when all is said and done, after canceling, I were to get 72 degrees. Most people don't have an issue with that. Here's what people get messed up. Convert to degrees, and I give them this, 5.24. How do I convert to degrees now? I can make it a fraction if I want. What am I going to multiply by if I want to get to degrees?
180 over pi.
180 over pi. Now, in your soul, that's uncomfortable. Because you're like, wait a minute. If I want degrees, I know to multiply by 180 over pi, but the pi doesn't cancel. Well, that's okay. Where is the pi? It's already in there. Like, think about it. If I take 2 pi over 5, isn't that like 6.28 blah, blah, blah over 5? If I were to multiply that out, isn't that something like 1.25-ish, right? This is a fraction of a radian. Not all radians have a pi in it, because remember, a radian is measured, it's part of a circle just like 360. It's just a weird reflection in that it's a decimal. 2 pi all the way around is a decimal that never terminates and never repeats. We write it with a pi to be nice sometimes, but sometimes that radian measure, it's going to be a decimal. Now, when you see that, don't freak out. And by the way, how do you even know it's a radian? Because there's right? And I'm not going to be dirty and put something like 135 that looks like a degree. And I'm like, sorry, psych, I left the degree bubble off it. It's really a radian. I'll give you something that's unusual looking, right? And hopefully as kind of a trigger that you'll go, oh yeah, wait a minute, I don't recognize that. That must be a radian. So multiply by that the same way. And then at this point, I don't know, that's a pretty ugly number. I can't see anything that cancels. I'll make it easy. How about 5.2? You'd have to come over here and multiply the 5.2 out. Right, 0.639. 1 decimal place means I have 1 decimal place. So this would be something like 936 over pi degrees. And if I didn't have a calculator, I would leave it like that. I'd be good with it. Normally, I probably wouldn't. If this is a rounded decimal, I'd probably just find the actual decimal equivalent of that, which is probably something like, what, when I divide 900 by probably 300 something in that neighborhood, when I divide that by 3.14. So that's like a 300 degree value. It's just weird looking. But don't be intimidated by that stuff. Remember, if I want to end up with radians, pi radians over 180 degrees, let the degrees cancel. If I want to end up with degrees, 180 degrees over pi radians, let the pi's and the radians cancel. And again, sometimes there's no pi to cancel. Don't worry about that. Just bring it along if it doesn't cancel out. And that honestly is a very missed question right there. Mainly because people probably don't go back and review it or they don't take notes or whatever. But make sure you remember this. Make sure when you're using those formulas, like theta equals S over R or any of these, if you use these directly and you're using a theta, you've got to convert to radians first or it won't make any sense to you. Got with me? Okay, last couple things. This is not a huge day of learning. That's going to come tomorrow. What I want to talk about are trig functions. I think you maybe know a little bit about trig functions. Like, does anybody here know what a sine function looks like if you graph it?
It's like a wave.
It looks like a wave, right? Or a cosine. Anybody know what a cosine looks like? Cosine's actually also a wave, but instead of starting here and going up and then down, it starts high and goes down and then up. But that's just assuming it's a basic trig function. We're going to ugly all these trig functions up, and we're going to shift them up and shift them down like we did with parabolas. We're going to shift them right, shift them left like we did with parabolas. We're going to stretch them like we did with the parabola, except stretching them just makes it look higher and lower as opposed to skinnier. We're going to pull them out this way and make the periods take a long time to finish. But what we talk about with trig functions are they're periodic. And when I say something has a period, that means it has a cycle to it, okay? And it takes a while to complete that process. On a sine curve, it starts here and it goes up, back to the x-axis, and then below, and then back to the x-axis. And it takes a certain amount of time or a certain amount of x's, units, length, to complete that. And that length that it takes, and we're going to go over this a lot more tomorrow, is called what we call the period. And sometimes the period of a sine function will take 2 pi or like 6.28. Sometimes it takes 6 pi. Sometimes it takes a half a pi to fit it in. But it just depends. Sometimes you'll have what we call an amplitude, which is a height and a low depth to it. How high or how low it's going from where it kind of the middle is. All those things we'll talk about. But today we're not going to be talking about trig functions and periodicity or the length of the cycle. We're going to be talking about weird, just random functions. So you might be given something like this. Like, let's just pretend for a moment that I gave you a function and I said one period of the function, I'll label this 1, 2, 3. What if I said one period is drawn, can't spell, below. And I said, draw another period. Well, another period would mean, okay, if the period is the length of 3, that means I'm going to take this picture and keep repeating it after that forever and ever. So what would I do to draw this next one? Well, if I started here on this one and went up, like, I don't know, let's say that's 2. Well, it looks like a 3. So I went up 3 over 1. Well, I'm going to, again, start back here and go up 3 over 1. And then over here, it looks like I went over from 1 to 2. Then I'm going to go over here from 4 to 5. And then over here, it looks like I went down a little, maybe down 1.5 over 1. Well, I'm going to go down 1.5 over 1. And you can see that the same period got repeated, right? Y'all with me on this? Well, and if the thing continued, I would say something like, all right, graph this graph from, I might say graph it from -5 to 5. So if I say graph it from -5 to 5, then you would go, well, I don't even have to graph that last part, but I got to go all the way over here to -5. Now, how am I going to go this way? Same kind of thing. If I started the period here, then I would have to pick up the other one where the end was there on the right. I'm going to have to put that here on the left. I'm going to go up, over, down. Are you seeing that? It would be a little bit better if I drew these to scale right here. Once again, start there, up, over. Now I would have gone down, but since it says only go to -5, we'll stop right here. But can you see that this thing is repeating its pattern? Yes, no? Okay, so if it asks you to, if it gives you a part of a function and says, hey, there's the period, sketch this from a so-and-so to so-and-so, that's what they're asking you to do. Okay, another thing they're going to ask you to do that I need to discuss first, and we've already mentioned this once before or twice, we're going to talk about even and odd quickly again. What do you remember about even and odd functions? Okay, so even functions have y-axis symmetry. So I'm going to mention that that is a characteristic of them. That is actually not the definition, but that is a characteristic that's really important. What do you know about odd functions? They have origin symmetry. Do you remember? Y-axis symmetry is linear symmetry. So you basically are doing a reflection across the y-axis. But what is origin symmetry doing?
Like one quadrant.
So you're kind of like you're putting a nail in there at the origin and spinning it how much? 180. So usually stuff that's in like the first quadrant ends up in the third, because you're taking it and rotating it around. Stuff in the third ends up in the first. Stuff in the second ends up in the fourth. You are with me? So you got to visualize it going all the way around. But the visualizing is great, especially if you have kind of an artistic sense to you or a spatial sense to you. If you stink at that, what's the definition of even? So this has origin symmetry. This is a characteristic. Origin sim. But what is the definition? Even functions all have this property that what?
Positive on the right and negative on the left.
It's possible, but what's more important is that opposite values of x give me what?
Even.
Same y values.
Yeah.
And that's the only way I can get symmetry, right? An x on this side, an x on this side gives me the same y, or an x over here gives me the same y. It would have to be that way if they were flipping about the y-axis. Does that make sense? So how you write that is opposite x's, x, negative x, have the same y. Positive, positive, or negative, negative, doesn't matter. That's the definition of even. And if you really think about that, it makes sense, because look, positive x, negative x, same y value. Positive x, negative x, same y value. Positive x, negative x, same y value. And you can see a function maybe like this one would be symmetric, but opposite x is same y. Opposite x is same y. Odd functions. What do we say? Opposite x values this time don't give you the same, they give you opposite y values. So how do I make an equation of that? How do I say opposite x's?
F at x equals,
I'll say
or
f
f at
x.
negative x equals negative f at x.
F of negative x equals negative f of x. Yes. So basically, in order for them to be equal, I would have to negate the y value of one of them to make it equal the other one. But that's how you say opposite x's give you opposite y's in that statement. And yes, if you think about that, look, opposite x's, like x and negative x, they give me opposite y values. And you have to be like a rotation about the origin. So graphs that had opposite x's, opposite y's, opposite x's, opposite y's, you would see that in graphs like x cubed, y equals x cubed. So what if I did this then? What if I went back to this equation? Tell you what, I'll do a different one. What if I went back to this function and I drew this? that's 1, 2, 3, 4. And I said, one period of F is drawn below. And if you're trying to sketch this, just make that the point. That's 0, 0. That point is 1, 2. So that point right there is the point 1, 2. That point right there is the point 2, 2. I'm back down there at 3, 0. And that point right there is the point 4, 2. So what if I gave you that, or the book gives you that picture, and they said, sketch F from -4 to 4 if F is even.
And you
Ooh, okay, so -4 to 4. Here's your 4. There's your -4. What do I do if it's even?
reflect it over the y-axis.
Opposite x's, same y's. So if that point is 1, 2, then I should also have what? -1,
1, 2.
2. I should also have
Negative
-2, 2. I should also have
-3, 0.
-3, 0, and
4, 2.
-4, 2. And then if I just connected it, you would see that mirror image. Opposite x's, same y, right? And then what if I just change that from even to odd?
Then it would go like the y-axis, like
Then what?
-1 would be -2.
So now opposite x's would have
Opposite y.
opposite y's. So if I make the x opposite, the y's got to be opposite as well. So -1, -2 would be somewhere down here, right? And then -2, -2, and then -3, that would still be 0 because I can't negate a 0. And then -4, -2. And you would see something like this. And again, doesn't that look like it had been rotated about the origin? Now, what if I said, okay, sketch F from -8 to +6 if F is odd and one period of F, no, if F is even, no, forget the even and odd. How about this? Sketch F from -8 to 6 if one period of F was given. So I'm going to go back and I'm going to get rid of everything. So nothing about even and odd on this one. One period is given. I want you to sketch it from -8 to 6. So there's -4, -5, -6, -7. So there's -8, 5, 6. How do I sketch it from -8 to 6 if only one period of F was given?
You do the period, but you like cut it off.
So I just got to keep marking these periods to the right and to the left until I just get to where I need to be, right? So what do I do for a period? If I went up, across, down, up,
Go back to 0.
go back to here and go up.
Wait, would you do 1 over? Because that's the.
Well, that's one period, right? So if one period has a length of 4,
Oh, okay.
I got to repeat that again, right?
So like for one x coordinate, there's 2 y coordinates for that point.
That's actually a good observation. If this was a function, that would not be able to be true. Do you hear what he's saying? So in this case, I can tell you what the book probably does. The book probably gives you one where they connect, and that's not an issue. But that's a great, excellent point. In this case, I would probably have to have given you that,
Okay.
so that it would remain a function. But I think the problems in your book, when you start the new period over, they probably are connected.
Okay.
So you don't have that issue. But wait, notice that. Yeah, if this is going to stay a function, it would still have to pass that vertical line test. So at this point, I could say up, over, down, up, but a length of 4. So up, over, down to 7, and then up. But I didn't need to go that far, so I would just cut it at 6, because that's all I needed on the right. And then over here, what do I do? Going this way, I'd be going what? Down, up, over, down. So I'd have to start high, right? And go down, up, over, down. You see the period repeating itself? Don't flip it around. If you do that, you're turning it into an even function. Didn't say anything about that. And you're getting rid of its periodicity. Periodicity has to look exactly the same from one period to the next. So again, open circle, down, up, over, down. So from -8, assuming that was equal, you'd have a closed right there, the end right there, no open circles, but you can see repeated, 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 and then repeated as much as I can squeeze in. Y'all see that? And honestly, that might be the extent of what you're going to be asked to do, but there's one last thing I want to talk about in the next couple minutes. And this is something that's kind of a math king topic that shows up a little bit. And if I didn't mention that, I got an email from her saying that she's hoping to have the results out by Friday. So there's a chance she might get them out. If at the very minimum, I can just, if you're out of here by the time she sends them, I can just send, I'll just send the Schoology messages out with a link to it. And you can go check out and see how you did, or how we did. But we'll see. Last thing. There are times when you're going to be asked to multiply. They're going to give you stuff like this. F of x is even, is an even function. All right, so f of x is an even function. They'll say something like g of x is an odd function. And then they'll say stuff like h of x is neither even nor odd. Now, do you remember what an even function means? What? Opposite x's have
the same y.
Same y, right? Odds, opposite x's have opposite y. Well, what happens if I take an even function like f and I multiply it by an odd function like g? And then I ask you, what is the result of an even times an odd? And that becomes a little tricky. So let me talk about rules. Whenever I am adding an even plus an even, and see if you can notice some patterns, I'm going to get an even. Even plus even, even. If I'm ever adding, and this is also true for subtraction, if I'm ever adding, I'm not even going to write these functions. I'm just going to write here from here on out. An even added or subtracted to an even, even. An odd added or subtracted to another odd is going to be odd. With the exception is if you subtract an odd from itself, what happens? You get 0, and 0 would be even. Because y equals 0 is a horizontal line. All right, but if the odds are different, okay? That's true for addition, subtraction. Okay? And if I ever have an odd added to an even, then it's neither even nor odd. So examples of that would be stuff like this. Examples. If I have like an x squared plus an x to the fourth, even, even, even. If they're both even and you're adding and subtracting, even. Something that's odd and odd, 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 odd. They're both odds, you're adding or subtracting, you end up getting an odd, okay? But if I ever have something like a odd plus an even, odd plus even, it is neither even nor odd. And you can see that if you graphed it. If I plug 2 in there, I get 8 and 4 is 12. If I plug -2 in there, I get -8 and 4 is -4. I plugged in opposite x's. Did I get the same y's or opposite y's? No. But if I do that here, opposite x's still give me the same. Opposite x's give me opposites. Those check off. Those are rules for adding and subtracting. Now, totally different from multiplying and dividing. And by the way, remember, sometimes trig functions are thrown in there. Do you know which trig functions are even? We've talked about it. Cosine and secant, those are the only even ones. So I could change this up and go cosine plus x to the fourth. Is that even or odd? And you'd go, wait, cosine's an even function. It's one of those where Whether I plug in an x or a negative x, I still get cosine of x. Doesn't matter. Opposite x is the same one. Even, even, even. I could do something like this. Odd, tangent, that's odd. Odd, odd, odd. All right? Now, when it comes to multiplying, check these out. See if you can see the pattern. If I'm multiplying or dividing, doesn't matter, or dividing, even, 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 odd, odd, even, odd, even, odd. Does that feel? Do you have another way of explaining that? Or thinking about it?
Like positives.
Like positives and minuses, right? Evens are like positives. Positive times a positive is a positive. Odds are like negative. Negative times a negative is a positive. But if they're different, odd, negative, positive, negative. Y'all seeing that? So what if I gave you something like this? A function is x squared plus x to the fourth over tangent of x. And I go, is f even, odd, or neither? What are you going to do? Well, what do I have here on the top? An even power and an even power? Because you can see if I plug a negative x in there, it's going to go away, right? So opposite x is same values. Adding two evens give me an even. And what is tangent? An odd function. And then now you're down to dividing. What happens when you take an even and odd and you divide? It's like a plus and a minus. It's minus. So this is an odd function. And I don't even have to check it. If I lost all these rules, could I walk in here and go, well, let me just plug in like 30 for 30 degrees and then negative 30 for negative 30? And if I get the same y value, it's even. If I get opposite ones, it's odd. And if I get something totally different, I either made a mistake or it's neither. I didn't have to do that, did I? I didn't have to go through the mess of that because I just went, wait, top's even, bottom's odd, even divided by odd's odd. And you're going to see some of this as well. And the one trickiest part about this is the neithers. Here's what's weird. A neither multiplied by a neither or divided could be neither, could be even, or could be odd. And we're really not going to know unless we do it. I can give you an example. Here's a neither, an odd plus an even, right? What happens if I take that neither and divide it by this neither? I get even. Don't I? 1 is like 1 x to the 0. It's even. And I could do other really weird manipulations or something and get odd. Here's an example.
Wait, so
X to the 4th plus x cubed. This is a neither, right? Even, odd. This is a neither, even, odd. But if I factor an x out of this, what happens? That cancels and I get odd. Who knew? So if I were to give you words like, what does a neither times a neither give me? You can't answer like you can here. You'd be like, I don't know, dude. Depends on what you have. Most of the time, a neither divided or multiplied by another neither is going to give you just some other neither. But you don't really know. But these are little things I might kind of quiz you or check you on anyway, but I'll give you more practice with it. All right?
Can you just sign the sheet?
Yes, thank you. Stop doing it.
Really nice and circle that's basically yeah. A lot of things.